Hello, and we're continuing to look at the Higgs particle and understand some general issues about analyzing counting experiments. This is the last lecture on this topic. I'm Jeffrey Fox, and we will first recap what we did last lecture and discuss random numbers quickly. The most interesting feature about random numbers, as we use in that Python program when we called rand or randn, was they aren't really random. Namely, we did not actually have little sensors looking at nuclei decaying and counting that decay times and generating a random number that way. Rather, what computers use are so-called pseudo-random numbers, and they use our basic principle that if you take something pretty complicated and messy, then you often get random results. And in the case of pseudo-random number generators, the things that are usually messy are the low order digits of integer arithmetic. So here are some Wikipedia references. Basic one on pseudo-random number generators, one on the particular version, the Mersenne twister used in Python, and then an actual discussion of Mersenne primes of the form 2 to the p minus 1, which are actually used in that twister method. The interesting feature of pseudo-random numbers is they're totally deterministic given their starting point. Namely, they're generated in order. Uh, Given one pseudo-random number, you generate a new pseudo-random number determined by that original one, or possibly by, in more complicated version, by multiple original ones. And for those starting points, the numbers are completely determined. Some computer systems, not really computers, I mean runtimes, actually always use the same seed. So when you call them, you always get the same sequence by default. However, Python takes actually a more sensible assumption. It actually takes the seed from the time of day. That's actually a reasonably normal thing to do. I used to do that um, whenever it was 40 years ago when I started writing random number codes that use random numbers. And it's also pretty random. Namely, if you look at the time of day to enough accuracy, nowadays it's probably microseconds, but maybe they don't even go to that accuracy. It is a pretty random number, the digits forming that time. And so the Python generates this pretty random time of day seed, and then it generates sequences based on that initial value. In good old days, we didn't have terribly reliable random number generators, and we often used to prime the random number generator by running it a few thousand or tens of thousands of times and throwing away those initial numbers because they might have been biased. Because sometimes if you take a simple seed or the inappropriate seed, the first few random numbers are not really terribly random. This comes from the Wikipedia article on random number generators. And the simplest one, which is what I used to code up in when we say using C, was that you form a sequence of numbers just by taking uh, the current random number, multiplying it by an integer a, adding a constant c, these are all integers, and then taking the modulus with respect to a certain value. If you want to write simple code, 2 to the 32 is a nice modulus because that says if you take 32-bit integers, multiply them together, you get a 64-bit integer. And then modulus 2 to the 32 just means you take the low order 32 bits. So this illustrates the basic principle. When you do pretty complicated things like multiplying large integers, the low order bits of that result are basically random. The high order bits are of course not random because they're strongly correlated by the size of the things you're multiplying together. So Wikipedia has a list of values of these magic constants A and C, and also some of the conditions they ought to obey to get good answers. And these are the values for a well-known book called Numerical Recipes, which is a set of algorithms used in scientific computing. It also points out that in the bad old days, people used incorrect random number generators and actually got incorrect answers because if you're trying to, if you have a random number generator and the actual numbers are not independent, then all these nice rules like square root of n and things like that are incorrect. And you may not even generate technically the correct answer because if your random number, I mean, the simplest problem, which is annoying but not perhaps catastrophe, is that the numbers it generates are actually uniform over the range, but there's some correlation between them of that given one number, the next number tends to be near it or far away, or some digit has relationships. The worst example would be if the random numbers were not actually uniform. They tended to congregate in some part of the range. But now we know how to generate random number generators, and a decent library should have a decent generator. And as far as I know, the Mersenne Twister is an excellent generator and a good choice for Python.